Hey, Katie.
Hi, Ben.
What are we talking about today?
We're talking about the lottery ticket hypothesis, which is a
Oh,
really interesting way that you can win lots of money
yeah, I know about
by
that one.
buying scratch-off tickets.
Well,
No,
well,
it's a
actually,
it's a thing in neural nets.
oh, okay. I thought it was the hypothesis was that every time you buy a ticket, you will never win the lottery.
Well, that's not true.
That one's actually panned out pretty well for me. You are listening to Linear Digressions. Also, I don't play the lottery, so just disregard everything I said.
All right. Well, let's talk about the neural net lottery then, which you probably don't play also, but that's okay. So, lottery ticket hypothesis. This is a pretty cool result, I think. It's a research hypothesis that's gotten a decent amount of attention in the last year or so. And the rough idea is this. Imagine that you have a neural network that's doing, like, I don't know, let's say some image classification. Pretty standard thing for a neural net to do. And it's this big, complicated, deep neural network. It's got lots of hidden layers. They're all very densely connected to each other so that all of the neurons in one layer are feeding into all of the neurons in the next layer, and so on. And you're training this neural network and it's learning how to classify pictures.
Okay.
The lottery ticket hypothesis is the hypothesis, which is backed up by some evidence, that maybe it's not the whole network that is doing the heavy lifting on the classification task, but if you were able to introspect it a little bit, you would find that there's actually subnetworks within that big dense network. So only a small fraction of the actual neural network is in these subnetworks, but the subnetworks are the ones that are doing actually all of the heavy lifting around that classification, and a whole lot of the network is actually not really doing very much at all.
That's really interesting. So
Yeah.
I guess then I mean, are those subnetworks then the lottery tickets? Is that where it gets its name?
Yeah, so that's the idea, is that you have this big sprawly neural net that's got all kinds of junk and connections and weights and all these sorts of things in it. And then there's just a little slice of it, some small percentage of it that's the winning lottery ticket, if you like. It's hard to know in advance where it is, but we'll talk about how to find it and why people think that this is something that could be going on. But yeah, the notion is that you kind of start with this big pile of possibility in the form of this densely connected neural net, and then you as a researcher, when you're training it, part of what you may be doing is finding the winning lottery tickets inside of that big pile of stuff.
That's interesting. So as a software engineer, I'm very accustomed to thinking of systems as being designed, because that's what I do all day is I design systems and I write functions and methods and all of that. And so I know as I'm building it, and in fact, I specifically decide where the complexity lies. And what you're saying is that our neural network, we don't know where it's going to lie because we're not designing it. We're just feeding it with a bunch of data to train on, and then it's arranging itself in a way that it does this task really well, but we have no idea necessarily how. And you were saying that these subnetworks are a small fraction of the larger network, is the hypothesis.
Yeah.
Could it also be like 50% of the neural network that's doing this, or 70%?
Yeah, so let's talk about how you actually find a lottery ticket and why people think lottery tickets exist.
Oh, and just to clarify, when you say lottery ticket, you're talking about winning lottery ticket.
Yeah.
Because I'm certain lottery tickets exist. I've seen them.
Right. So when I say winning lottery ticket in the context of this episode, I mean the subnetwork within your big, densely connected neural network. It's the smaller subnetwork that is actually doing the heavy lifting when it comes to the classification task. It's the part of the network that's actually predicting things correctly.
Got it.
And the implication here is that much of the rest of the network isn't really doing anything. So let's unpack that piece by piece. Number one, how do we know that the rest of the network isn't really doing anything? Well, because these researchers basically came up with an algorithm for getting rid of big pieces of the network as part of the training process. Yeah, and this is something that, well, we've talked about it a little bit before in the episode about dropout, which I know was a while ago. So I'll refresh real quick, but it's roughly the idea that as you are training your network, you are getting rid of some of the connections as you go. And maybe you're just getting rid of them randomly. Or in this case, what they're doing is as they're training the network, if they find that the weights are small, then they set the weights to 0. The weight being the connection between one individual neuron in one layer and an individual neuron in another layer. So you have many weights in the whole thing. And some of them are taking on large values, which tells you that there's kind of a lot of signal passing through that part of the network. And some of them are decreasing in value, or they have very small values. And those are the ones that, in this case, they would be setting to 0 as part of the training algorithm.
Okay, so you take your range of probabilities, or your different probabilities within each neuron. You set the low ones, the ones that are under some threshold, I guess, that you tune to 0, and then you redistribute that small probability over maybe the remaining connections.
Yeah, I think that's about right. I don't know if there's that step of explicitly redistributing the rest of the weight, but I think that's probably a minor detail. Effectively, I imagine that if you keep training it, it kind of does the same thing. But yeah, you set them to 0 and then you lock them in at 0, which is effectively getting rid of those connections. So it's a parameter of the algorithm, what percentage of the weights you want to set to 0 in any given iteration. But each time you pass it through, you're reducing the connectivity of your network by whatever that percentage is.
Okay, so you're basically taking your algorithm as you're training it, you're getting rid of the weak connections, and I guess I'm assuming that if you have weak connections, that means that probably that connection is not very involved in the algorithm making a successful prediction. And so effectively you're getting rid of the parts of the algorithm that are not doing much in terms of predicting.
Yeah, and the thing that you're doing at the same time too, usually when you're training, is that the connections that are remaining, the ones that are, winning the horse race here to get to stay in the neural net, their weights are moving around as well. So they might be going up, maybe in some cases they're going down. But one thing that's worth pointing out here that I've implied so far, but we'll just make it explicit, is that when you start out with training your neural net, you have to set those weights to something. And so usually what people will do is they'll just initialize them randomly. So there's this notion of the initialization of your neural net as being a thing that you have to think about. You have to start somewhere. That's what your initial conditions are. So as you're training, you're, of course, moving away from those initial conditions. Some of the weights are going up, some of them are going down or being set to 0. And the thing that's curious here, to my mind, is not exactly that you can prune away some of the weights and have the remaining neural net be pretty strong. Like, that seems not that strange. The thing that's interesting and why they call it the lottery ticket hypothesis is, now let's imagine that you get to the end of this whole training and pruning process and you have maybe 20% of the connections left. Now take those connections and set them back to their initial values, the ones that they had before you did any training. You've gotten rid of the other 80%. Those are gone, but we're going back to the initial conditions for the 20%. Now see how good your neural net is? It's pretty darn good. It's like almost as good as it was when you trained it. And it's just the initial conditions again.
That feels really unintuitive.
Well, and this is why they call it the lottery ticket hypothesis. So the idea was, you had this subnetwork. It was like the 20% or whatever of the connections that you found. And those were like the good ones to begin with. You won the lottery when you initialized those weights to those values. And what you're doing when you're training your neural net is not necessarily like sculpting it into this thing that's learning anything from the data. Instead, you're selecting the parts of it that were really good at recognizing the data to begin with.
Oh, I see. Wait, can I just rephrase this in a way that makes sense to my brain?
Please.
And tell me if this makes sense to your brain. But so there's kind of this analogy of a neural net to an actual brain, and obviously this doesn't hold up in so many ways, but if I were to just run with that metaphor for a moment, or that analogy for a moment, it's kind of like you just randomly create this brain with neurons connected to neurons semi-randomly, or maybe entirely randomly. And then you go through this process where you figure out which connections that have been randomly connected are meaningful connections to accomplishing a task. And then you just sever all of the other connections. And that on its own is enough. You don't actually have to like connect any neurons in particular ways or anything. You can just sever the connections that don't seem to be helping you and leave the connections that seem to be coincidentally very good for your task.
Yeah, I think that's right. And, the thing that I would just accentuate here is that, at least in this context of neural nets, you don't have to be doing really anything additional to the ones that you leave behind. You just have to leave them behind, and they'll do the lifting for you. And part of the reason that we know that this is the case is that they did a bunch of experiments about what is it that you do with the connections that are left. So do you let them keep their final weights? You're like, okay, yeah. And then the neural net does a good job of identifying the pictures. Like, we've trained it to do that. So that's not super surprising. We talked about what happens when you set it back to the initial weights, which is that it does surprisingly well. And then the other thing that they tried was they kept the connections that were found, but they set them to new random initializations. So they didn't set them back to the ones that they had at the beginning of the training process, but instead they picked some other bunch of random weights and assessed how well the algorithm did with those weights. So the idea here is it the connections that are special, or is it the connections in combination with the weights that they have? And so when they set it back to a random initialization that was never part of the original training to begin with, then all of the performance that they saw totally fell apart. So they know that the initial conditions were actually a really important part of, the secret sauce here.
Oh, interesting. Okay, so it's not just the connections, but it's the weight of the connections. Both of those things are important.
Yes.
Interesting. Ooh, I wonder what would happen if you, instead of taking out the connections that didn't work, what if you took out the connections that did work?
Well, so it's interesting. There was an initial paper from a couple folks at MIT in, if I'm not mistaken, March of 2019. So this is 10 months ago now or so. And then there was a follow-up paper from a group at Uber in their research department that was taking this initial lottery ticket hypothesis and exploring a bunch of different permutations that you can put on the algorithm to try to understand, like, okay, does it have to be set to 0, or can it just be set to small? How do we define exactly which ones get pruned? How aggressive can we get with the pruning before it starts to really actually fall apart? So they were doing a bunch of different variations on this, trying to understand it a little bit better, and potentially thinking about stuff like, how can we find winning lottery tickets more quickly, or do they have special attributes that we can try to engineer, these sorts of things. So anyway, we'll have links to both of these papers at lineardigressions.com, and you can dig into all of these details. But to your point, I wonder if they tried this, or I wonder if they tried that. The Uber group, in many cases, did some of these interesting follow-ups in the quest to try to understand these a little bit better and to really put as fine a point as possible on our understanding of what's going on here.
Okay, so then you're saying that there are kind of 3 ways to get a well-performing neural net, at least that we've talked about here. One is just train it like normal. Don't prune away any connections. This is business as usual. 2 is train a neural net, set the weak links to 0, and then just use what you get at the end. And then the third is do that, but at the very end, set the weights of the remaining connections to what they originally were. When would you use these? Do the latter 2 perform better than the original one? Or are there any benefits to using one over the other?
That's a great question. So in terms of the accuracy that you get out of sort of the best version of each of those, I think they tend to plateau at about the same point. The thing that's interesting about the pruned away neural network with the the original initialization in place, so not the weights that it learned, but the weights that it had originally, is that it's actually a very compact way of expressing a neural net. So they're very small compared to a big neural net that's got lots and lots of parameters that you have to describe, each of them individually. That's the first case. That's the biggest in terms of, the memory footprint or how many bytes it takes to store this on your hard drive. That's the biggest one. Now, in the second case, where it prunes away a whole bunch of the connections, and then you have the connections that are left, those have the learned weights in them, then it's much smaller than before, because maybe you've gotten rid of 80 or 90% of the connections, but the 10 or 20% that are left, you still have to describe them each individually. But the thing that's cool about the third case is you've gotten rid of 80, 90% of your connections, so winning there. And then the second thing is that usually these initializations are made with like a random seed in a random number generator inside of your computer. And that random seed is deterministic. So if you put any starting value into the seed, it'll come up with the same set of pseudo-random numbers that it generates for you. So that means that you can effectively pass the architecture and the random seed when you want to hand off the model, and then somebody can regenerate the whole model from scratch. And it's very compact compared to either of the other representations, which is,
oh, wow.
In terms of accuracy, like I said, you're doing roughly the same in terms of accuracy as the other two, but it's a lot smaller, which is kind of nifty.
So just to repeat that, basically you pass some representation that says, hey, these are the connections that I kept. And then you also pass instructions for how you generated all of the random numbers in the first place, which can be extremely small. I use this method in this library or in the library that's, on all of the machines that this might be running on. And this was the number I started, the number I seeded the algorithm with. So that's all you have to pass. And you don't have a model that's ready to use, but you do have instructions on how to relatively quickly generate that model so you can use it.
Yeah, that's right. And I guess the other thing I should add here is this is kind of what we've come up with after less than a year of even knowing that lottery tickets could exist or that they do exist. So one can imagine that as we study them some more and use them to gain better insights into what successful neural nets are actually doing, there might be more applications of these to come. Who knows? But right now, at the very least, it is a quicker, cheaper way to get basically the same performance out of these big, super heavy neural nets that, everybody's kind of laboring under the weight of them, which is, pretty cool. So to sign us out, I'm going to tell a brief personal story, which is I also do not play the lottery. But one time when I was in third grade, I went and visited my cousin and my aunt and uncle, and they lived in Canada, and I played the Canadian lottery, which was technically, if I understand correctly, illegal because I was 8 years old.
Oh, jeez.
But I played the Canadian lottery, and I won $2 Canadian, which was less than $2 American. It's $1.50 maybe at the time. So
wow.
I was in third grade. That was a lot of money.
Did you, how did they send the money to you? Did they issue you a check or something?
No, it was just like in a convenience store. So they just gave me in Canada, they have the $2 coins. They're called toonies. And I got a little Canadian toonie.
That is
And then
awesome.
I think I bought some candy with it.
Well, I have not yet won the lottery, but maybe someday I will if I buy a ticket. Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.